Okay, here we go. We're going to go ahead and do 2.3 today, talking about the definition of continuity. It's an important definition, one that should be on a note card, and something that you need to be able to not only memorize, but use correctly and not forget by the end of the year, because sometime in May, last 2 years in a row, there's been a definition of continuity question on the free response sections. Doesn't mean it'll be there every year, but if you don't know the definition of continuity correctly, you end up losing some points. So, here we go. What the heck is continuity? Well, before we got to this class, we said continuity was, I can draw a function without lifting up my pencil. Okay, well, that's an awesome definition. We're not going to ever use it again. Okay? So what do we got going on here? Well, first of all, here's some 3 graphs, and we're going to talk about just some general principles. Types of discontinuities here, we could have a hole where we literally removed a single point from the graph, but the rest of the graph looks normal. Where you could have a vertical asymptote, VA, or we could have what we call a jump, okay? Where we literally are not connected from one side to the other. And notice that the jump has a hole on the top and a solid dot at the bottom. That's going to be distinguished between simply removing a single point. The reason there is a hole here and a solid dot here is that if we had a solid dot in both of them, it would fail the vertical line test and therefore not even be a function. So we have basically those 3 types of discontinuities. We're going to lump them into 2 categories, removable and non-removable. Okay, so these are the words we want to remember. Use those other ones to help you out. All right? Basically, if a function is not continuous, but I could make it continuous by appropriately defining or redefining f of c, we say that f has a removable discontinuity. What does that mean? That means we have a hole in our function. Okay? The only type of removable discontinuity we're going to deal with is a hole, and so this function right here is going to be removable. If there happens to be a dot right here above that, that's okay. It's still a hole, but the definition says if I can make this function continuous by filling that hole with a point, a single individual point, then I've made it continuous. And if I can do that, it is a it is a removable discontinuity. Otherwise, it's non-removable. Vertical asymptotes, I cannot fix with one point. I don't care where I put this point, it's not going to fix my continuity issue. Okay? Over here, I don't care if I put it here, 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 or somewhere in between, it's not going to fix my continuity issue. I have to move lots and lots of points. The only one that I can fix with a single dot is the one with a hole that someone has plucked out of my function. So the only one that has a removable discontinuity is the first one. And let's continue, okay? Let's talk about this graph. Find the points at which the function below is continuous. And when we ask for continuity, we're talking more about intervals. And what we look for is where is it not continuous, okay? So when we look at this graph, we can see that at x equals 1, there's a removable discontinuity. At x equals 2, it looks like there is a vertical asymptote. X equals 3 looks okay. And x equals 4 looks like we have a jump. But everywhere between those integers, 1, 2, and 4, we seem to be continuous. So we're going to say things like this. It is continuous on the intervals from, let's go ahead and say, from 0 to 1, but not including 1. It is continuous from 1 to 2, but not including 2. It is continuous from 2 to 3, but not including, well, actually, all the way to 4, but not including 4. And then it is continuous from 4 to 5, but again, it's not continuous at 5. I'm sorry, it's not continuous at 4. We'll go ahead and say that it is continuous at the endpoints, but really it means that it's continuous on the right and the left side only, okay? It's continuous from the right. There is no domain issue, or there's a domain issue here, left of 0 and right of 5. We won't spend too much time worrying about that right now, okay? But it's continuous there. So what kind of discontinuities we have? That means it is discontinuous or not continuous at x equals 1, x equals 2, and x equals 4. And at 1 we have a removable discontinuity. At 2 and 4 we have non-removable discontinuities. The only one I can fix with a single point is the discontinuity at 1, and that would require me to take this point and fill that hole and redivide that single point into a different place. I don't have to do that, but I could, if I did that, it would be continuous at 1, therefore removable at 1. Now, this is the most important part of your day, right here, okay? we have a definition of continuity. We're going to see how this works in just a minute. But what does it mean for a function to be continuous in calculus? It means it fits that definition right there. That is all it means. And when I say, what's the definition of continuity? You write, the limit as x approaches c of f of x equals f of c. Okay? But that means a bunch of things. It means that not only does the limit exist, and that limit is only going to exist if the left and right limits are the same, and this part is on the next page of your notes, I think, but the limit is only going to exist if the left and right limits are equal. So if you have a function that is broken at a certain point, or you're evaluating it to the left and the right of a specific point, the limit will not exist at that point unless the left and right limits are equal. Now, just because the limit exists at a point does not mean it's continuous. And this is the part that everyone forgets. They always forget to check to make sure or verify that the function value at that point really does equal the limit. Or they check it and they don't write it down. I don't know which one. But it seems to be missing on a lot of papers. We get so caught up in doing this part because that's where all our work is involved, but no one ever seems to remember to check. I won't say no one, but a very few, a small minority of people remember to check that. So it's very important that you remember that in order for this to work, the limit has to equal the function value. In other words, I could have a graph that went like this with a hole in it, okay? And as x approaches c, the limit goes up here, the limit exists. But if there's a hole in the function, that can't be continuous. It doesn't work. So we have to make sure that the function value at c is not up here, but actually in that hole right there and not somewhere else, or not even existing. So it basically says three things. Number one, it says the limit exists. Number two, the function value exists. And number three, they happen to be the same. Okay? If it's a piecewise function or you're evaluating something from both sides, remember to check both sides of your limit to make sure it exists and check the function value. Okay? Let's see how this works. All right. We've got our last picture here. For 1, 2, and 4, we had points of discontinuity. All right? Let's take a look at the limit as x approaches 1 from the left of my function. Let's take a look at the limit as x approaches 1 from the right on my function. And let's take a limit as x approaches, oh, I'm sorry, that's just terrible looking, f of x. Love the board here. Really getting tired of it. Okay, and we really want to find f of 1 as well. Okay, so f of c, limit, limit, limit. All right, the limit as x approaches 1 from the left side. Well, as I go to 1 from the left, my function values are getting closer to 1 on the y-axis. As I approach 1 from the right side, my y values are approaching 1 on the y-axis. Well, that means if the left and right limits are the same, the function value approaches 1 as x approaches 1 for both sides. But the problem is, the issue here is that f of 1 is defined way up here to be 3. So it's not just good enough to check the limit. The limit as x approaches 1 of f of x does exist. It does equal 1. But f of 1 is 3, therefore the limit as x approaches 1 of f of x does not equal the function value at 1, therefore it's not continuous at x equals 1. Let's check c equals 2. First of all, f of 2 does not even exist. There's a vertical asymptote. There's no y value when x is 2. Therefore, it can't be continuous. It fails automatically just by checking the function value. Okay? If we were to check the left limit, we would say the limit as x approaches 2 from the left of f of x, it would actually end up equaling positive infinity. And so would the limit as x approaches 2 from the right. I'm not going to write it down. Okay? Partly because the board is just bothering me completely. Okay? But the limit as x approaches 2 from the left is negative, or is infinity. The limit as x approaches 2 from the right is infinity. So this does not exist either. Okay? The limits do not exist because the function as x approaches 2 grows without bound. All right? How about at x equal, or c equals 4? All right? Well, the limit as x approaches 4 from the left of my function happens to equal 3. And the limit as x approaches 4 from the right of my function equals 2. That means that the limit as x approaches 4, I'm going to write it up here, of my function does not exist. Okay? And if the limit doesn't exist, continuity fails. All right, you could argue that f of 2 or f of 4, just for fun, happens to be defined at 2, but if the limit doesn't exist, it doesn't matter if the function value exists or not. 3 things that have to be checked. Does the limit exist? And in order for it to exist, you got to check the left and right limits a lot of times. Okay? And then you got to check the function value and then verify that they really are the same. All right? Don't forget any of those pieces. All right, so how are we going to do this without a picture? Well, we've got to rely on some of our understanding of domain, vertical asymptotes, holes, and all that fun stuff, and then talk about what's going on, okay? So whether or not each function is continuous here, and if it's not continuous, let's use the definition of continuity to explain why. Well, our domain issues, we know that the denominator of our fraction, x minus 1, cannot equal 0, which means we know that x cannot equal 1. So our domain issue right away tells us that we're going to have a problem at x equals 1. All right, so what does that mean for us? Well, in order for us to show it's not continuous at x equals 1, there's going to be a vertical asymptote here, okay? We have to use the definition of continuity. Well, we can, this fails for lots of reasons, but we could just say simply that f of 1 is undefined. Therefore, f of x is not continuous at x equals 1, because the definition of continuity says as you approach any number, the limit has to equal the function value. Now, we could have checked the limit. We could have said that the limit as x approaches 1 is actually going to turn out to be positive or negative infinity, depending on which side of 1 we approach. It's not going to exist either. Either way, this is going to fail for all kinds of reasons, okay? Our second problem is going to have the same basic issue. We have a domain issue at x equals negative 2. We say x plus 2 cannot equal 0, which means x cannot equal negative 2. Okay, now just to see what's going on here, this numerator actually would factor. All right, we get 2x and x, and then we're going to get a 3 and a 2, and that's going to be plus, and that's going to be minus. And what we see is we could cancel this out. So g of x is actually going to look like a line, except for there is a hole. There's going to be a hole in your function at x equals negative 2. Well, what that means is if you were to check the limit as x approaches negative 2 of g of x, you actually could evaluate the limit at 2x minus 3. It's going to equal 2 times negative 2 is negative 4 minus 3 is negative 7. But, big but, g of negative 2 is undefined. And again, if the function value is not defined at a specific point, you can't have a continuous function. Okay? Therefore, g of x not continuous. All right? It can't happen. You have to have the limit equal to the function value at that point, or it doesn't work. Okay? Let's try the next one. Here, unlike before, I have what basically amounts to a line and a parabola. So individually, these pieces are going to be fine. Polynomials are continuous everywhere. Lines, parabolas, cubic functions, all right, they're all just fine. The issue is going to be what happens at x equals 1. Okay? The other ones were easy. We had vertical asymptote, we had a hole. It was very easy to talk about the fact that it wasn't defined. The function is not defined at those points. Can't be continuous if they don't have a definition or defined point at that point, at those individual x values. Now, here, at every x value on the planet, it's fine, except for maybe at x equals 1. And let's check this, okay? So at x equals 1, we want it to be continuous, which means the limit as x approaches 1 of my function h of x has to equal h of 1. That's the definition of continuity. However, this limit only exists in this function if the left and right limits are the same. So we're going to actually rewrite this to say this. This may seem tedious, but it gets you full credit. All right? So as x approaches 1 from the left, we're evaluating this function, which is negative 2 times 1 plus 3. And I would suggest you write that down so you have indicated you have evaluated 1 from the right side, or from the left side, and not the right. As x approaches 1 from the right, we get 1 squared. Now, h of 1 is different because h of 1 is only going to be defined for one of them, and it's defined when x is equal to 1, so we actually get 1 squared again. Now, these two are the same, so I'm not going to write it over and over again, But negative 2 times 1 is negative 2, plus 3 is 1, equals 1, and you could write equals 1 if it makes you feel better, which checks out. So according to our definition of continuity, the left limit of h of x equals the right limit of h of x at x equals 1, and it equals h of 1. Therefore, h of x, sorry, don't need to write the limit again. Therefore, h of x is continuous. All right? And my board from about the last 3 inches down is just horrific right now. All right? But we're going to live with it. Okay, so that's how we use the definition of continuity to show that something's continuous or not. All right? Now, one of the things you get every once in a while is these little parameter type problems where you've got this extra value of a in here and you've got to figure out how to make it continuous. And there's nothing wrong with the skill involved in just making up numbers, playing around with it, but we have to at some point algebraically show on paper what the final answer is, not just pull a number out of a hat or other places that aren't as pretty, and make sure we can do this on paper. Okay, so definition of continuity. Every time you see that, you probably should write it down. And if I'm breaking this apart at x equals 1, we're going to go ahead and say the limit as x approaches 1 from the left of g of x has to equal the limit as x approaches 1 from the right of g of x, and it has to equal g of 1. Okay? Same idea as last time, except for this time the question is not, is it continuous? The question is, make it continuous. Maybe that's not a question, but who cares? All right, what do we do? Well, as x approaches 1 from the left, we are down in this function. And remember, it's x that's approaching 1, so this is 1 plus a. As x approaches 1 from the right, we are on the top function, and we get 1 squared plus 7. And g of 1 happens to be the top function, so we get 1 squared plus 7 again. It seems redundant, but at least you can say, hey, I checked both of them. We don't really need to write that twice. We're going to focus over here. So we have 1 plus a equals 1 plus 7, which is 8, which makes a equals 7. It is not okay, however, to ignore this. If you don't write it down, I understand that in the process of solving this, we've set both of these equations equal to each other. But we did so because of limits, and we did so because of the definition of continuity. We didn't just set them equal to each other. The biggest mistake people make is they start right here, and that's all they write down on their paper. They get a equals 7, they high-five themselves, they move on, and they only get about half credit or less. All right? You need to make sure that if you didn't do any calculus, you probably didn't do the problem right. And the calculus is involved using the definition of continuity, which says the left and right limits are equal and equal to the function value. So somewhere on your paper that has to show up. All right, a equals 7 in that problem. Let's move on. Okay, let's see here. Same idea. The difference is here we have an interesting setup. X does not equal 1, but x does equal 1. This is where we don't actually have to do the left and right limits, because the limit as x approaches 1 of h of x has to equal h of 1. That's the definition of continuity, but I don't have to break the limit into 2 pieces, because as x approaches 1, it does so from both the left and the right sides, and that takes care of this top half of my function, because x doesn't equal 1, which means you can approach from either side. So I end up with 1 to the 4th minus 1 over 1 minus 1, which happens to be 0 over 0, which means do something else. Dang it! All right, so what are we going to have to do here? Well, we're going to have to factor this somehow, okay? Well, lucky for me, I remember how to factor. I look up here and I say, you know what? That's the difference of 2 perfect squares. So let's take the limit as x approaches 1. That's really x squared plus 1 times x squared minus 1 all over x minus 1. Well, that didn't help any, but this second factor is also the difference of 2 perfect squares. So I have the limit as x approaches 1 of x squared plus 1 times x plus 1 times x minus 1 all over x minus 1. And by the way, I think I just wrote this down and didn't mention it, but h of 1 happens just to equal k. So this whole thing is going to equal k every time, fitting our definition. Once I have these factored, I can cancel like factors, removing my 0 over 0 problem, and now going back to evaluating my limit as x approaches 1. That gives me 1 squared plus 1 times 1 plus 1, and the whole thing is going to equal k. Well, 1 squared is 1, plus 1 is 2, and 1 plus 1 is 2, and 2 times 2 is 4. So my value of k to make this function continuous is simply 4. All right, everything we've done in Chapter 2 all rolled up in one single problem. Don't you like it? I thought it was pretty cool. All right. Let's change gears for just a couple minutes here. intermediate value theorem. This is a very easy theorem to understand. What you have to do is remember that it exists so you can use it sometime. We're going to abbreviate it IVT. At some point in this year, there's going to be an IVT, an EVT, an XVT, an MVT. There'll be a couple of them, and they usually show up all in the same problem. So you really just need to understand what they are and how to use them, just what their conditions are in order to be used. That's the most important part. Okay? They don't tell you how to find anything. They tell you whether things exist. These are called existence theorems. Okay? And what the intermediate value theorem says is if, and this is important that you pay attention to this, the hypothesis is if f is continuous on the closed interval. That's all that has to happen. As long as the function is continuous on a closed interval, the rest of this is true. All right? F takes on every value between f of a and f of b. All right? Now, seems simple enough. Suppose k is any number between f of a and f of b, then there is at least one number c in a, b, in the closed interval a, b, such that f of c equals k. Doesn't that make more sense now? All right, probably not. All it means is if you're here one moment and you're here the next, as long as your function is continuous, this function says you must hit every single y value between this point and this point. It doesn't matter if the function goes like this. All right, so that's not a function. All right, terrible. All right, or it goes nice and pretty like that. But you have to hit every single y value between the bottom of that interval and the top, or f of a and f of b. Okay, so understand this a little bit. What are the necessary requirements to apply this theorem? Well, number one, f is continuous on a closed interval ab. K is on which axis? Well, in this little statement, suppose k is any number between f of a and f of b. Well, that means k is a y value, so it's on the y-axis because it's between the function values. All right? It says then there is at least one number, which means it could happen more than once, but there's at least one number in the interval AB. So where does that put C? Well, C is on the x-axis, such that the function value at that x value of C is equal to K. All right? So if that wasn't clear as mud, here we go. Here's a picture. Is F continuous on AB? Check. That means the intermediate value theorem is allowed to be applied. Plain and simple. Is K between f of a and f of b? Well, I have labeled f of a and f of b. Here's f of a, it's the y value right there, and f of b is the y value at the other side, and K is some y value between them both. So yes. In this particular example, how many times does f of c equal K? In other words, how many c values are there between C, remember, is between A and B. How many of them give me a y value equal to K? Well, in this case, there are 1, 2, 3. So there are 3 C's. How many does the intermediate value theorem guarantee me? One single answer. But at least one. 3 is at least one. Okay. So label them as C1, C2, C3. So this is C1, this is C2, this is C3. Now, finding them involves algebra. You have to solve equations. You have to set one side equal to the other, solve however you wish. But guaranteeing their existence is done through the intermediate value theorem. Let me show you how this works, because we're not actually going to find any of these answers. We're just going to tell whether they exist. I have this function, x squared plus x over x minus 1. Verify that the intermediate value theorem applies. Well, how do I verify that it applies? Well, I have to make sure the hypothesis is correct. The hypothesis is f continuous on the interval 5/2, 4. That's the question. That's supposed to be a 5/2. There we go. All right? Well, this function has a discontinuity, discontinuous. Basically, it has a vertical asymptote at x equals 1. But we don't care what kind of discontinuity. We just care the fact that it's discontinuous. At x equals 1, but 1 is not in my interval. X equals 1 is not in the interval 5/2, 4. So the answer to this question is yes. The intermediate value theorem is applicable. Big words for me. All right. So what do? Well, we just simply test the left and right side because we want to explain why the intermediate value theorem guarantees an x value of c, where f of c is 6. And that c value has to be between 5/2 and 4, by the way. So what we're going to simply do is plug in 5 halves and plug in 4. We plug in 5 halves, and I end up with 5 halves squared, which is 25 fourths, plus 5 halves over 5 halves minus 1. Oh, this is exciting. All right, so that's 25 over 4 plus 10 over 4, so that's 35 over 4, divided by 5 halves minus 2 halves is 3 halves, which means I have 35 fourths times 2 thirds. That cancels with that, and I get 35 sixths. Woohoo! All right, we'll come back to that in a minute. F of 2 then, F of 4 is 4 squared plus 4 over 4 minus 1, which is 16 plus 4 is 20 over 3. Okay, now 35 sixths was going to be 5 and 5 sixths, and 20 over 3 is going to be 6 and 2 thirds. All right, so how does this guarantee me an x value where f of c equals 6? Well, the intermediate value theorem basically says that as long as this value of, as long as your function is continuous, let me start over. As long as the function is continuous on the closed interval, and the left side of the interval is 5 and 5 sixths, and the right side of the interval ends up at 6 and 2 thirds, then this function hits every y value between them, between the 5 and 5 sixths and 6 and 2 thirds, at least once. Is 6 between 5 and 5 sixths and 6 and 2 thirds? Absolutely. Okay, so since f is continuous on the interval 5 halves comma 4, and f of 5 halves equals 5 and 5 sixths, and f of 4 equals 6 and 2 thirds, the intermediate value theorem guarantees A, and I'm going to erase this so I have more room to write because I'm running out of room here, guarantees a value of C between 5 halves and 4, where the function value of that point has to equal 6, because 6 is between your y values here. Okay, so I think that's going to do it for 2.3.